Okay, all right, now that we've got the basics down, let's take a look at some of the possible reaction pathways. We can sort of categorize these reactions into two classes. We've got the ones where you have a strong nucleophile and the ones where you have a weaker nucleophile. All right, if you have a strong nucleophile, what will happen is that the nucleophile will directly attack the carbonyl, drives a pair of electrons up to the oxygen so that we get this intermediate here where we've got, this is an oxonium ion where you've got a negative charge on the oxygen. All right, then what you have to do in a separate step, you have to protonate this. All right, and you can do that either with aqueous acid or with just water itself. All right, and the result is that you protonate this oxygen, you turn it into an alcohol, and this is your final product. Okay, this is the type of reaction that you're probably familiar with a say a Grignard reaction, a Grignard reagent. Now, if we're using a weaker nucleophile, what we've got to do is we've got to activate this carbonyl. All right, and one of the best ways of activating the carbonyl is by protonating it. All right, so in this step here, what we're doing is we're starting kind of, we're sort of reversing the order of this previous reaction in the sense that we're going to protonate the oxygen first. Okay, now by protonating the oxygen, we generate a positive charge on the oxygen. That makes it even more electron withdrawing, makes the carbonyl carbon more electrophilic, and as a result, more reactive. Okay, so this is the pathway that we have to follow whenever we're trying to get a weaker nucleophile to react. If you have a strong nucleophile, like say a Grignard or a strong base or something like that, you don't have that problem. Okay, the base will be, or the nucleophile will be strong enough to hit it and attach to the carbonyl on its own. Okay. There's an added complication here, and that is that if we have any kind of a nucleophile that has extra electrons, like extra lone pairs, like for example, if we had an amine, which I'll show you in a little while, all right, what will happen is you get a reaction called an addition-elimination reaction. All right, and we'll go through the mechanism for that later on. But basically what happens in those addition-elimination reactions is that you actually boot out this oxygen. Okay, you boot out the oxygen, you replace it with the nucleophile. All right. Now, as I say, I'll show you a couple of specific examples of this as we go through this. Okay. All right. Okay. So with an example of a reaction involving a weak nucleophile would be the formation of an acetal or a hemiacetal. Okay. And as I said before, in order to get this to work, and alcohols are not particularly strong nucleophiles. All right. So in order to get this reaction to work, what we've got to do is we've got to sort of energize this or activate it by protonating this first. So this reaction will take place in an acidic medium. Okay, and we get a hemiacetal. We'll have more to say about that a little bit later on. Just to go back to the scenario that we have with a strong nucleophile, we have a Grignard. Okay, Grignards are extremely powerful nucleophiles. All right, so this doesn't have any trouble at all. As a matter of fact, you've got to take precautions with a Grignard. You have to make sure that it's not in a protic medium. All right, if you have a Grignard in a protic medium, what will happen is it will act as a base. All right, and it'll pull the protons off, and it will not act as a nucleophile. It will act as a base. All right, but anyway, it follows a similar pattern. All right, so in this case here, we've got this alkyl group. All right, and the end result is that the alkyl group comes in, attaches onto the carbonyl. All right, then we protonate the oxygen, and we end up with the alcohol. This is another type of very important reaction involving carbonyls. It's called a hydride reduction. Okay, if you recall, we said that hydrogen can exist in several different forms. Okay, it can be a proton, in which case it doesn't have any electrons. It can be just a plain hydrogen atom or hydrogen molecule, or it can be this hydride ion. These hydride ions are extremely powerful nucleophiles, and this is the way we actually reduce a carbonyl to an alcohol. All right, so this is kind of like in the same family as Grignard reagents, because once again we've got a very powerful nucleophile comes in, hits the carbonyl, drives a pair of electrons up here, and in the final step we protonate the oxygen so that we end up with the alcohol. Okay, probably one of the simplest reactions involving weak nucleophiles is hydration. All right, and actually this reaction synthetically is not very important. I mean, it's not a very useful reaction, in terms of making other compounds. But it was very important for theoretical purposes because a chemist by the name of Jenks made extensive studies of these hydration reactions, and he, by doing that, he was able to elucidate a lot of the, the basic chemistry of these carbonyl compounds. All right, but essentially what happens is this: you do it in an acidic medium. Okay, so the first thing you do is you protonate the oxygen. All right, you get this, and in the next step, what happens is that having protonated this and having activated the carbonyl, the water molecule can come in and it can hit this, and we get this little diol. These things are not particularly stable. And as I said, they're not very useful compounds, but they are interesting from a theoretical point of view. All right. We can also do the reaction under basic conditions, where in the case of a base, you don't have to do any kind of, well, you can't do any protonation. I mean, you can't have an acid and the base in the same system. But here, if we use hydroxide is certainly strong enough as a nucleophile, because it's basic, to come in and successfully attach itself onto the carbonyl. Same thing happens. Okay, it comes in, hits this, drives a pair of electrons up here, and then in the final step we protonate the oxygen, and we end up with this diol. All right. As I said, these are not particularly useful reactions, but they are kind of instructive as to how the basic mechanisms work. Okay, and as we said before, the reactivity of these things, in other words, the tendency to form these hydrates, it all depends upon steric effects and electronic effects. And this is just sort of like a ranking of the reactivities in this reaction, forming hydrates throughout a group of typical carbonyl compounds. Okay, so once again, the formaldehyde is the most reactive, and then we get this ethanal. All right, this is less reactive because you got more steric bulk here. And also this ethyl group is going to donate more electron density, and it's going to sort of deactivate this carbonyl carbon to some extent. Okay, and then if we stick these electron withdrawing groups, it's going to make it even more reactive, so on and on it goes.